Testing, testing. Okay, no feedback. So I think, well, good morning. We had completed Gauss's law last, or introduced electrostatic flux and derived Gauss's law on Monday. And I do want to continue to illustrate the power of Gauss's law with some specific examples that we're going to work out to find the field pattern using Gauss's law. Problems that would be difficult, much more difficult using Coulomb's law in order to find the fields of these charge distributions. But before I do that, I think I need to go back and clean up a couple of points from the end of the last chapter on the electric field. So I'll do that before going, and then at the second, and then we'll go back to Gauss's law and work through some of those examples. I'm going to start with a section I call a charged particle in a uniform electric field. So we had done work where we talked about Coulomb's law. We defined the electric field early on a few weeks ago, and extensively found the electric field distribution of certain charge, electric field of certain charge distributions. But I want to go back and look at the definition of the electric field and make some, in a sense, analogies, ultimately we will, with the electric field and the gravitational field. I've already done that to a certain degree, but we can continue that process of comparison. So we define the electric field with respect to the electrostatic force. We say that a field, so this is going to be charged particle in a uniform E field. Okay, so we said that electric field E is equal to electrostatic force divided by the charge that is being forced upon. So the idea with this definition is that we can think of a force on a charge Q naught as being originating from the field in a region of space, as opposed to from some other specific charge or distribution of charges, which is the way that we initially looked at force on a charge, right? Now, if that's the case, then so with this definition, we can then define it's not a definition of force, but it's a description of force in terms of field, as opposed to in terms of a series of other charges. And we can simply see that the force is going to be equal to the charge times the value of the field. Now, mathematically, that should look a little familiar to you in terms of the form. We've seen something like that before, particularly when we say uniform field, we mean that E field is constant. And the analogy that I'm making is with Newton's second law, basically, either weight or free fall motion, for example. We see something like that, right? Net force is equal to a constant, in this case, mass times an acceleration. And if that acceleration happens to be the acceleration due to gravity, then we can say that, like, for an object in free fall motion, then we can see that the force is equal to mass of the object times g, where g is a constant field in the region. So the same thing, similar situation. We can think of the force of two massive particles coming from, force of one particle on the other, and vice versa. Newton's third law and the universal law of gravity. Or what we do when we were considering free fall motion, we really weren't considering the Earth, so to speak. We were considering the field near the surface of the Earth caused by the Earth. And that was the thing that was accelerating the object as the object fell. Right. So we can kind of do something similar to that with the electric field, or think about it in that way. Excuse me. Yeah, so we are comparing E to G in terms of the effect of the G field on a mass is analogous to the effect of an electric field on a charge. So if we want to know, if we use Newton's second law, basically, and the definition of E together, that is equation 2 and 3a, we can equate those. And one really nice illustration of how this can be set up is we can set up a charge in a uniform field, but the uniform field could be created with capacitor plates, for example. We can have, well, I'll get to that in a minute, but yeah. And so if we have capacitor plates setting up a field and we have the charge in the field, charge can behave very similarly to that manner in which a mass behaves in a gravitational field. So to determine the acceleration on the charge in a constant field E, we can just equate equations 2 and 3. And what we see is that the acceleration then of a equating equations 2 and 3a, we get that Q naught times E is equal to M times A. So for example, if this were like the mass of a proton, then that equation would become E, the value of a, the elemental unit of charge times E times the mass of a proton times the acceleration that the proton would have in that field. So taking the absolute values, we see that the acceleration of that particle would be equal to the charge divided by the mass, the ratio of charge to mass, times the value of the field. So equation 6 would give us the value of the acceleration of the charge of a charged particle, in this case, the proton, in a uniform electric field. So let's look at a couple cases here. In case 1, we're going to have an electric charge. So a couple case studies. Let's say that we have an electric field pointing along the x-axis, and we set up our coordinate system in the following fashion. Where we have the x-axis along the horizontal and the y-axis vertical. And we're going to place say a proton down here at the origin. And we're going to start it, we'll place it there at rest. So I'll just put MP, meaning that that's a proton. Of course, it has charge E. Remember, E is equal to 10 to the negative 19, 1.6901 times 10 to the negative 19 coulombs. So we know the charge and we know the mass of the object, and we set the electric field up so that it is pointing along the positive x direction. Now, very similarly to how we would illustrate the gravitational field in, close to the Earth, where we would just put a little symbol and a vector up at the corner representing G. We can do something like that here. We can say that in this whole region of space, there is an electric field. It's a constant field and it permeates the space. But as opposed to drawing all those constant field lines, we'll just do something like, the electric field is pointing to the right in the x direction, and its value is EX, and of course its direction is I. So that represents the vector field E, right? Or EX, I guess we could denote it. So everywhere in this space, we have a constant field pointing in the x direction. So at time t, how far has my charge traveled? So we can say for case one, assuming a proton is placed, actually, at the origin with initial velocity 0, how far has it moved and what speed does it have at at time t? What is the speed v and position x at time t? So note that I've used the explicit time dependence of these variables. And so, yeah, so obviously, if it's in a uniform field, it's going to have a force on it. The force is equal to this guy here, Q times Q naught, well, actually E, this E times capital E. And so it's going to accelerate. It's going to accelerate along the x direction for a positive charge. Positive charges move in the direction of the field because field lines point from positive to negative. So whatever is setting up this field is the direction from which the field is pointing. There are positive charges there, so you can think of it in terms of the properties of a charge is that like charge repels. So the positive charges is moving along the direction of the field away from the positive charges, which are the origin of the electric field. See that a little bit more clearly when I illustrate this with from a point of view of a capacitor. At any rate, we have this. What's given here is the initial position, the initial velocity, and the time. And we want to know the velocity and the position at a later time. So to be clear, what is given, what is known in terms of explicit and implicit information is initial position, x naught, which is equal to 0, v naught, which is equal to 0, and time. So for accelerated motion, how do we do that? Well, we've got 4 equations of motion for accelerated motion. Remember those? V of t is equal to v naught plus a times t. X equals x naught plus vx naught t plus 1/2 at squared. And of course, v squared equals v naught squared plus 2a delta x, and delta x equals 1/2 vx plus, or v naught, you could put the x in, I guess, vx, x naught times t. So in order to get v of t and x of t, it's pretty much a plug and chug, right? particularly after we've already calculated the acceleration. From Newton's second law, we have that the acceleration is equal to E mp over E. Right? So if we go with the first equation here, the initial velocity is 0, and putting in equation 5 into 1, I guess I should have kept the numbering going here. Let me do that. So I guess I don't need to rewrite that then in that case. So 7, so 6, 7, 8, 9, 10. So we've determined the acceleration here. The initial velocity is 0, we plug it in. So the velocity at any other time t is going to be equal to E over mp times capital E, all of that times t. So that would give me my velocity at some other later time t. And you can see it's constant, right? So if the field is constant E, then the velocity, the function is a constant. This is a linear curve, right? This has the form y of x equals mx, and of course, the b in this case is 0. So if we were to graph that, we would get a linear function. And so you know that a line, the slope is constant. And the slope of the velocity versus time curve is acceleration. So the slope of the line that you would graph is this constant term that is multiplying the independent variable t. So that's the velocity. And as far as position is concerned, we could go with equation 8. Both the initial position and the initial velocity are 0, as we said. So this term is 0. This term is 0 because that's the initial velocity there. And so what we see is that the acceleration, the position is equal to 1/2 at squared. So equation 12 here, we get that x of t equals 1/2 at squared. And again, substituting equation 6 into equation 12, we get that the position is equal to 1/2. Well, let's make that E times capital E over 2m p times t squared. And based on the analogy that I made over here, you can see what that has the form of a parabola. The linear term and the constant term are 0, but still y of x equals a times x squared, where b and c. You remember the equation for a parabola is a squared plus bx plus c, but in this case, the a would have been x naught and the b would have been vx naught. Those were 0, so this gives a simple parabola. The simplest, one of the simplest forms of parabola. But the a in this case is going to be e over 2mp. So, yeah. And all of that is very similar to, a mass in a gravitational field. We've seen, parabolic in time, free fall motion. And of course, for constant, it's also linear. The manner in which the velocity changes with respect to time for free fall motion or any kind of motion where the object is experiences a constant acceleration. So this is no different. We're kind of combining some of the concepts of electrostatics with Newton's dynamics and kinematics. So I hope that's clear. and helpful for you. I didn't point those out. That usually this stuff is tacked on to the end of the chapter for electric field. So I'm pretty sure it's in your chapter there. I realized somehow my notes got scrambled and I went on to flux without mentioning these little points. And actually, I think it's pretty straightforward. So if you read through that, you probably got something from it, I hope. But still, I should go over it in class, so it doesn't take that long. So I'm just presenting this stuff here. Also gives an opportunity to review some of the concepts from last semester as well. Now, the next thing I have here is we looked at a dipole moment. We looked at the field of a dipole moment. We defined dipole moment and used that as a jumping off point to set up the integral for a thin line of charge, looking at the symmetry between those two charge distributions, dipole versus thin infinite line of charge, to be exact. So we know what a dipole is. I'm going to go back and take a look at dipole so we've taken a charge and put it in the electric field and looked at some of the repercussions of that, the motion. Let's take a dipole and put a dipole in an electric field. I think I did explain to you that one of the purposes of defining a dipole moment is that if we have the moment, we can think of the moment as being, we can deal with the moment as opposed to dealing with the individual charges. Creating a dipole moment really looks at the result of external influences, field forces, that sort of thing, on the combination of the positive and negative charge. Now, remember a dipole moment now it has its own field, but in an external E field. And we will assume that the field of the dipole is negligible with respect to the external field. Um, yeah, dipole, what? Sorry, I just lost my train of thought. Um, Sorry about this confusion. Notes. Okay, sorry. what was I saying? Yeah, so I guess the way to visualize this thing is that, so let's say that we have a dipole situated like so. So I guess I'm just going to draw. I don't really need to draw a axis, so to speak, but maybe we'll make a vertical, maybe a one-dimensional axis. And you don't have to call it, it's just a line. You can call it Y if you want, but just whatever. And we're going to take a dipole. Now remember, a dipole are two charges, a positive and a negative charge, that have the same polarity. Sorry, the same magnitude, but opposite polarity. So we're going to set this up so that we have a positive charge here, and then some distance d away, we have a negative charge here, so that the length of the dipole is d. And now, remember the electric field pattern, I could draw it, but along the line between the charge, the field, as I said earlier, points from positive to negative. So it's doing like this, right? So that's E, in between the charge. Now remember, there's more to it than that, right? E actually looks like this guy. It's all that stuff, doing that, coming out, and up here it kind of goes out like that. And then down here it comes in like that. So in the field line points always toward the negative charge and away from the positive charge. So we have all that stuff there. So all that's there, but I guess I could keep it there. I don't want to get it too confusing. But what we found is that the dipole moment, so this is a dipole, but we define something called a dipole moment, where the dipole moment is equal to, in fact, let's make sure we distinguish the distance between the charges. As I said, as d, but let me indicate that on the diagram. So if that is distance is d, we defined a dipole moment as small symbol we used was p. It's a vector, and it's equal to negative 2. And remember, if each of the charges has a value of q, that's minus q and that's positive q, they're the same value. You can say q plus and q minus. And keep in mind that the magnitude of q plus equals the magnitude of q minus, just equals the magnitude of q. Is q. Then the dipole moment was defined as minus 2q times d. And the minus sign indicates that the dipole moment is pointing in an opposite direction relative to the field. So the dipole moment exists between the charge, between the two charges, and it has a, if I were to represent it vectorially, it looks like this. So that is P in the electric, P. Okay. Now, what's useful about the defining the dipole moment is effectively if we have evaluated the system such that we understand the orientation in the field and the magnitude of the dipole moment, we can kind of effectively forget about everything else. In other words, I can redraw this picture like so. We can deal only with the dipole moment. Just easier, more practical situation to deal. We have a dipole moment, and we can think of like pinning the dipole. So even though the charges are not pinned to their position, the dipole is pinned so that we could think of the, I'm going to blow this up a bit. So we can think of the dipole moment here. Okay, that's P. And we can think of like kind of pinning it at a point so that it can swivel. So it can't translate away from being the center of the dipole, and of course also the dipole moment has to be localized at some specific point halfway between, well, it can be anywhere, but in this case, let's just assume that it's halfway in between the dipole, right? So that even though it can't translate away from that region, it's allowed to pivot, like so. And so we can just think of the dipole moment as pivoting. So we just take all that other stuff away. All that stuff is still there, but we can just focus on this. Now, this field here, let me be clear. This is the field of the dipole. So I'm going to put like field of, I'm going to write it in terms of the moment. So sure, it does have a field of it by itself. But in the same way that we neglected thinking about the mass of an object falling in a gravitational field, right? This thing has its own field around it, and it's like a point charge. It's like pointing in toward, toward the object. But when we talked about objects falling, in close to the surface of the Earth, masses, we never talked about the gravitational field of the object, and you probably never thought about it, but it has its own field. In other words, if I were to conventionally show in the way we would show it back then is, we have the ground, for example, we have a mass and it's falling in, from some height h to the ground, like one of the classic problems I start physics 37 with is I start with that, and the mass, the height, and I drop it from initial velocity of 0. How fast is it, moving just before it hits the ground, and what is the time in which it takes to fall? And usually I do something like this. We know that there's a constant G field in that region, and it's pointing down. Now, if I were to show the field everywhere, it actually looks like this, right? But that's kind of messy, so we just kind of put it over there someplace. But what I'm trying to say is that, and let me make this a bit better. Let's make this a circular object, like a ball. So if that's a mass, this thing has its own gravitational field, and the gravitational field is pointing in, toward the center of it like that. So in the vicinity of, technically speaking, in a vicinity very close to that mass, it distorts the constant gravitational field because, as you know by now, gravity abides by superposition. So everywhere close to this mass m, the field is a combination of the mass of the field of the mass m and the field of the Earth. So technically speaking, the field is going to look something like this, right? If I superpose those fields and here's my math. So gravity I don't know, it's going to probably do something like, ouch, it's not really going to be constant in the area around this mass. It's going to probably do something like, you know, and that's a extreme exaggeration, which is why we don't pay attention to it, right? So it's not really ideally constant. Um, as you get closer to the mass in question. But in the same way we assume friction to surfaces and that sort of thing, we assume that that's what we mean when we say the field of the mass itself is negligible. It's as if it doesn't exist. So even though this thing has a field and we spend a whole lot of time talking about it, we could expose it to a very strong external field, a constant field. And so if I do that and represent this dipole as being in that field where its own field is negligible, then similar to what I've just illustrated there, I'm going to have an external field that is, permeating the region of this space of around this dipole, and it may look something like the following. Just to make it interesting, I placed it at an angle relative to the vertical, which I can define. So this is now to distinguish between the field of the dipole E sub P, as I did here, I'm going to call this an external, E external. And yeah, we're making some angle, we'll call it theta, with respect to this vertical here. So this angle here, extend this one down. That angle is theta. And so effectively it's making that angle initially with the initial position of the dipole. Now I say initial position because, as I told you, this dipole is pinned so it can swivel. It can swivel about its central point here. And it will. Why? Because the dipole moment has a, well, the moment, the dipole moment, has what we call a torque exerted upon it. And that torque essentially is the result of the force on each of the individual charges. Because now what we have is, when we think about the force on those objects, because we think of the object as associated with a dipole, that is, they are a unit or a system within itself, not individual charges, and it's like a rigid body, right? The charges cannot move relative to themselves. So think about, if I take small balls and place on the top of this thing, it's like my positive charge here, my negative charge here. The position of the charges don't move relative to one another. But think about it. If I have an electric field, and I don't want to draw it here, it's going to make it too messy. But if I have an electric field here, we know, we just spent a lot of time talking about the fact that the electric force F is equal to Q, the charge, times the field. But in addition to that, because of that, I talked mostly about magnitude in the last section when I was deriving the acceleration. Well, force is a vector. So what about the direction? Well, the force gets its vector nature from the field because the field is a vector. Whenever the charge is positive, the force points in the same direction as the field. But if I have a negative charge here, that introduces a negative sign. So the force is 180 degrees opposite of the field. Meaning, when I expose, and I know it's, just keep in mind that this electric field I have over here, and I might use some notation similar to what I did with G. If I take this, represent that in this first picture here, that my field is pointing everywhere in this region at that angle, like so, the external field. So I'm kind of just putting that notation up there in the same way I had G in the corner of the free fall problem, just to give us a visual to gauge in my next point that I'm going to make here. Whenever the electric field is, the force is whenever I have a positive charge, the force is in the same direction as the field. So on this positive charge, if I have a switch and I turn on the field, then this charge sees a force in that direction parallel to the field. So it's going to have a electric force on it, F, in that direction. We'll call it F positive, where F positive is equal to Q positive times E. And the negative charge will have a force on it opposite the direction of the field. So again, along the same line, but pointing in the opposite direction and with equal magnitude. Why? Because, well, E is constant, so it's the same E. And if the charges have the same magnitude, then the force will be the same magnitude, namely QE. But because of the negative sign, the force on the negative charge is pointing 180 degrees opposite the force on the positive charge. Now, remember that the dipole is pivoted, is pinned in the center and rigid. So when you have a force on the charge here pointing in that direction, a force on the charge here pointing in that direction, it causes the dipole to swivel. It gives an angular, basically an angular acceleration to the dipole, which causes it to spin. And we know that if a force gives rise to a linear acceleration, then a torque gives rise to an angular acceleration. So essentially, by placing this dipole moment in an external electric field and cutting on the field, pinning the dipole at the center, allowing it to swivel, when I cut on this field, I cause the dipole moment to swivel and pivot around. So we can you know what, actually I should have. No, it's fine. It's fine. Yes, I can do it like this. Yeah, so yeah. So that's first point. Now, let me show you something. There is a point where basically the way that I set this field up, as soon as I turn it on, the dipole has a torque and it's not the torque is not zero. But in this, let's go to this picture here. As this thing pivots, the torque essentially decreases. Now we'll quantify that in a minute, but just qualitatively, let me show you why. Well, in fact, let's just start let's go to this position here. Whenever the dipole is like this, now remember the positive charge is here and the negative charge is here. Now, when it's at that position, what is the force? What is the direction of the force on the positive charge? Well, the direction of the force never changes. So like here, if this represents the direction of the force as the object pivots, the force is still going to be pointing along the direction of the field. Its component along the direction of motion of the angular, position of the charge is diminishing. In fact, when it gets to this position, there is no net, well, there's a force. Let me put it this way. The force is not diminishing, but the torque is diminishing because of the angle. We'll show that in a minute. But the force is constant. It's constant in position and direction. That's why it doesn't change as the thing pivots. But the torque is changing. We'll review torque and show why that is in a minute. But just forget the mathematics of the physics for right now. Just look at your intuition. If I started with the dipole in this position and I turn the field on, this force is pulling the positive charge along the axis of the dipole, and same here with the opposite direction, the negative charge. So not only is there no torque, but the net force would be zero as well on the whole thing, because the forces are equal and opposite, so they're pulling against one another, so they cancel. So if I had started with the dipole moment in this position, when I turned on the field, nothing would happen. It would move. The only way it's going to move is if it's at some angle that's takes it out of its equilibrium position. So from this point, if I shifted a small angle down, then it's going to, the torque now, the force is still pointing in this direction for both charges. So it's going to try to right the dipole moment by bringing it back to equilibrium. However, it will now have an angular velocity and an angular momentum. So it doesn't just get to equilibrium position and stop, because it has momentum. So it shoots past, but then the torque changes its orientation and starts to decelerate the object, then bring it back and, overshoots again, and you go through one cycle of motion, and it just continues to do that. So you end up getting oscillatory motion. All right. Well, from the position that I started from, when I cut on the field, it's already some amplitude, delta theta, angular amplitude, away from its equilibrium. So I've set it up so that it's already in some sort of oscillatory situation. Because when I turn on that torque, turn on the field, it's going to start to accelerate it toward the equilibrium position, which is parallel to the direction of the field. But it certainly has it has momentum at that point, as I said, so it overshoots to an angle that's equal and opposite, as long as no energy is lost, of the positive angle that it started, from which it started. Decelerates, slows down, and that's a half cycle, goes back through another quarter cycle to equilibrium, and then goes back to a full cycle, which is represented by its initial position. So it would oscillate. It would oscillate in that way. Yeah, so we get oscillatory motion, and we get a torque on the dipole when it's exposed to, well, oscillatory motion as a result of the torque on the dipole when it is exposed to an external magnetic field. And also, because we've established an equilibrium position or equilibrium angle, that also implies that it has potential energy, right? That, again, if I started at the equilibrium angle and I displaced it from that equilibrium, that's akin to taking a mass and picking it up off the, picking it up off of the ground and doing work on it in the process, and in the process of doing that work, giving it potential energy, which it then tries to right itself by going back to its equilibrium position. on the ground. So when I expose this dipole to a external electric field, I create a situation where I can do work on it by displacing it from its equilibrium. And then when I let it go, it's at rest initially, but the work that I've done by displacing it through some angular displacement is now potential energy in the dipole moment, and it will try to fall back to its equilibrium position or rotate back. And now it's a different situation. It doesn't just, in the case of the object, it hits the ground, work is done on it by the ground, and it stops, and negative work, and it causes it to stop. But in an ideal situation here where there's a frictionless pin at the center and there's no other, there's no drag, it's in a vacuum, so there's no drag. Once I put work energy into that system, that dipole by pivoting it, there's nothing to take the energy out, and it would just oscillate on indefinitely. Yeah, so that's a qualitative description of what happens ideally when we have a dipole moment in an external electric field. And so we can quantify that. We can apply the concepts of torque and energy to this system and determine quantitatively what the torque looks like. And we can write that torque in terms of the dipole moment P. And we can also evaluate the potential energy associated with the dipole being displaced from an equilibrium position. And we can write that potential energy in terms of, again, the dipole moment P. So that's what we're going to do here in a few steps. And I think that's the last thing that I would do for this. Technically, this is in chapter 22, I think. They should have it in there. Yeah, in there somewhere. So at the end of the chapter, they'll do this. Okay, so excuse me. Let's do it. Actually, yes, it's break time. I think I need a bit of a break here. So let me take a little break and I'll come back. Okay, sorry about that interruption, and let's continue with what we're doing. So this distance is d, and the dipole is just the total distance between the charges times the charge, and of course the negative sign is there. So dealing with the magnitude here, since I've redefined that distance as d as opposed to 2a, then this is just d q times d. Now I've left off the minus sign because I'm just dealing with the magnitude here, and so this would be a negative q d. Okay. Yeah. Now, the definition of torque is that torque is equal to, the symbol we used was tau. Torque is R cross F. It's a cross product. And remember, you may remember with the right-hand rule, it applies in terms of the direction. So let's apply that to this situation here. Basically, if we look at, let's just redraw the dipole over here. Just a simplified version of all that busyness going on. So we've got the dipole, all right? It's pivoted at the center here. Let me just put a hole in the middle of this thing so I can use it. It's going to take too long to do that. But yeah, so this thing can pivot like that right now. What happens is I've got a force on it, and the force, well, two forces really, and the forces are here. That's F plus, and this is F minus. Now, in the torque, the R is defined as the distance from the pivot, the fulcrum, to the point where the force is applied. So for F plus, so basically we have two torques, the net, and also remember torque is superposition, right? So abides by superposition. So technically here, what we have is we have to evaluate the net torque, right? The the net torque is by definition the sum of I equals 1 to n of all the individual torques tau sub I. So, and again, remember the position vector. Now, some people refer to this as the lever arm, but that's not quite true. It's only the lever arm under certain circumstances within the motion of the system. But we would just call it R for right now. So I'm going to call this guy here R plus, and this guy R minus, associated with F plus and R plus, F plus and F minus respectively. And technically for this situation then, the magnitude of R plus equals the magnitude of R minus equals D over 2. I need to take a quick break right now. So I'm going to see if you can finish this derivation if you so desire. No one's there, but when you're looking at the video, see if you can try to finish the steps. Put these, think about these. Remember what you did with torque. Now I can help you a little bit. The net torque, when I write that out, I've got 2. Now keep in mind the right-hand rule. So you need to know whether these torques are going to add together or subtract from one another. Obviously, they add and thing pivots. You can see that intuitive from what we've already discussed. However, with the torque, right-hand rule, run, wrap, point. That's what I teach. Run your fingers like an arrow in the direction of the first vector. Orient your hands and then wrap your fingers so that your fingers are parallel to the second vector, but your forearm is still parallel to the first vector. So run, wrap, and then point. The direction of your thumb is the direction of the torque. So for F plus, the torque is into the board. Now remember, for a torque into the board, the rotation with your right hand will be clockwise. Torque is always in a direction perpendicular to the plane in which the rotation occurs. And that's the same for many of the angular coordinates. Direction for delta theta, the direction for omega, the direction for alpha, they're always perpendicular to the plane of the rotation. So here we're rotating in the plane of the board, but the torque is perpendicular to that. And the orientation of the rotation consistent with the right-hand rule would be counterclockwise, run, wrap, point. You can do the same thing with a negative vector, and you see that it's going to give the same torque, counterclockwise rotation. So here, the extension of equation 3 is going to be the net torque. I'll take the vector, we'll just do it mag. It's going to be equal to basically torque plus torque minus. They're going to be in the same direction. So see if you can finish that out and get a derive an equation for the torque in terms of the dipole moment. Go ahead and do that. I'll be right back. All right, back again, once again. So let's continue with this. We have to fill in, put in the plus and minus torques for equation 5. But to do that, let's go back to equation 2 and evaluate the cross product on each of the individual forces or individual torques. Well, I've already done the right-hand rule, so that's part of it. That gives the direction of each torque is into the board. Run, wrap, point. For this one, run, wrap, point. So both torques are into the board. When you know the direction of the torque, you take your right hand, not left, right hand, point your thumb in the direction of that torque, and your fingers will curl around the direction of the angular acceleration associated with that torque. So both of these torques are into the board, which means they have the same sign. They're adding together, not subtracting from one another. And they're both causing the dipole moment to pivot in the clockwise direction. So that's direction. Now, what about the magnitude? Well, from the magnitude, we just take it directly from the definition of the cross product. The magnitude of a cross product is equal to the magnitude of the vectors times the sine of the angle between them. We got to be a little bit careful here because the angle between them is actually them, meaning R and F. That angle, it's a little bit tricky with torque orientation. That angle is actually this acute angle here, where I've drawn in the picture. So the angle between F and R, because you either have to translate F back to the origin or project R forward. And we see that this actually is the angle that defines the torque. So with that in mind, torque plus is equal to the magnitude of R times the magnitude of F plus times the sine of the angle between them. I just call that theta. It is some arbitrary, whatever it was back here. I didn't define it specifically, but whatever, we know it. And the same thing for the negative torque. Tau negative is equal to magnitude of R negative, magnitude of F negative, times the sine of the angle between them. And it's the same angle because of the symmetry of the problem, of the symmetry of the physical situation. And so ultimately then we have so we add those together and we get and of course the R is equal and the F's equal. So basically we have the net torque magnitude is going to be RF sine theta plus RF sine theta. Remember that F is equal to QE. So, and R is equal to QD. Sorry, R is equal to, did I erase it already? I did, I think I had it over here someplace. R is equal to D over 2. So this R plus here, oh no, it's right here. R is equal to D over 2. So if we put all that stuff in, we've got D over 2 times F, which is Q times E, and sine theta, of course, plus D over 2 Q, E, sine theta. So got two of those, so you have two, cancel 2 times basically D over 2, Q, E, sine theta. The 2's cancel. That 2 there cancels with that half there. And we're left with Q, D, E, sine theta. Sorry, torque. And here we have our final result. Let's evaluate that. When you take a look at this, you see the QD is equal to the magnitude of P, and of course E is E. And if you take a look back at the dipole moment, what you realize here is that that angle theta, it's the angle between R and F, but it's also the same angle between P and E. Right, we showed it here. P is along, this is E, and this is P. So theta is that same angle. And so when you have, and again, P is a vector quantity, as is E. So what we essentially have here is P times E times the sine of the angle between them. And that is simply the definition of a cross product. When you have the magnitude of two vectors times the angle, the sine of the angle between them, then you can write that result as a cross product itself, so that we can write the net torque, and this was what I promised you would be the final result, is the torque in terms of the dipole moment. So we can say that the net torque is equal to P cross E. Which is an interesting result. Nice. Same, so we can box that in. So the net torque on a dipole is equal to the cross product between the dipole moment. The net torque on a dipole associated with an external field is equal to the cross product between the dipole moment and the external E field. And I should be careful here. I dropped the subscript about external. We want to keep that. Again, remember, beginning of the lecture, we're not talking about the small negligible field associated with the dipole moment. We're talking about the large external E field that really has nothing to do with the dipole moment, but is set up by some other circumstance, capacitor plates or whatever, what have you. Okay. Wonderful, wonderful. So that is the torque on the dipole moment. Now, I also alluded to the fact, or did more than that, I illustrated or demonstrated as a thought experiment early on that this thing also has potential energy. Once I displace it away from the equilibrium position, it has potential energy. So let's go ahead and derive the potential energy. And how do we do that? Well, the way that we always do. We calculate the amount of work done on the dipole by the external field. It is doing work. The torque can do work on a torque does work, and we have the relationship for that from what we did before with mechanics. So let's calculate the work done by the torque on the dipole, and in the process, we should be able to, we'll equate that work with the, well, we've already, there's a concept, the general definition of potential energy equates work with the negative of the change in potential energy. So we'll get the work, calculate the work directly from the definition of work for torque, and then we'll apply the general definition of potential energy, and that will give us the potential energy associated with this dipole whenever it is displaced from equilibrium. Now, I have to do work on the thing, but while I'm doing work to displace it, the electric field is also doing work. Again, directly analogous to what happens in a gravitational field. I can do work by picking this thing up, right? But gravity is pointing down, and so as I pick it up, I'm doing positive work, but gravity is doing negative work. And we calculate that work whenever we and we can calculate that work. So that's what we're going to do here. So the relationship that we used from mechanics for work of a torque is that the work done by torque, and I'm going to write this as a differential, right? Like, we can have a differential amount of work. I displace it just a little bit. Well, actually, if I displace it and then the field does work by pulling it back, you can break it up into little increments, of work throughout that entire angular displacement. So that's what I mean by differential work element. So 12, so D work, differential amount of work is equal to the integral of the torque times a torque over, times the differential angular displacement, d theta. Okay? Yeah. Now, the torque is, this is the magnitude of the torque, and we can take it directly from equation 10 or 11 there. So, sorry, actually, dW, and this is W for work, is equal to tau d theta. But when I integrate both sides, dW just becomes the work. So then the work is equal to the integral of tau d theta. That other thing I wrote, this is obviously not correct. All right. So anyway, tau, I take the magnitude of tau and I get it from over there, which is, so the total work as it goes from 0 to theta, whatever the displacement is going to be equal to P, the integral of the dipole moment times E times the sine of theta d theta. Okay. The dipole moment and the electric field are constant, right? Because I started by saying that we were placing it in a uniform field, so that's why E is constant. And the dipole is constant because it's comprised of Q and D, and Q doesn't change, and rigid body, so D, the length of the dipole, doesn't change. So it's a constant as well. So it comes out of the integration here in equation 14, and we can write work is equal to P E times the integral of sine theta d theta. And so it turns out to be pretty simple. Indefinite integral, the derivative of sine is negative cosine. Put in the limits to 0 to theta, which I didn't really put them in, but whatever, it's trivial. So what we're going to have is that the work, actually, no, is that, sorry, my bad. So, derivative of sine is positive cosine. Yeah, right. Oh, but no, there's three negative signs because it goes from, if it's displaced, final minus initial, so it's zero. Yeah, my bad. It's three negative signs. What I'm saying is, yeah, it's three negative signs. Let's take, so this is right. That's got to be, you know what? Now I'm confused. Just confused myself that quickly. What is the derivative of sine? I think it should be negative cosine. Derivative of sine is, sorry, not derivative, integral of sine. So the derivative of sine is positive cosine. So that's what was confusing me. I was thinking one thing and saying the other. So yeah, if the derivative of sine is positive cosine, then the integral of sine is negative cosine. That's right. And the derivative of cosine is negative sine, and the integral of cosine is positive sine. That's right. So the integral of sine is negative cosine. So yeah, I should make this an indefinite integral because, or a definite integral because that way I'm going to miss a sign. So when I integrate this thing, and that's where you'll see there'll be three negative signs with this, which will give me a negative. So to explain this, this is a little bit subtle here. I'm at equilibrium, right? So that's 0 degrees. But I'm going to displace this thing from equilibrium. I'm doing the work on that. So now I'm going to let it go. It starts from rest, and now the reason that it starts to move back is I've explained all that, right? Now the force is going to be put, but well, the torque, but the torque that's work. It's because there's, it took work for me to put it out here, so it's going to take work to bring it back. So the electric field is doing work through the torque as it goes back, but it goes from, so if you look at just this one cycle, the final position is 0 degrees and the initial position is theta. So here in the integral, you go from initial theta to final 0 in that cycle. Yeah. So here I'm going to, I get, now this is not potential energy. Actually, that looks kind of like potential energy. That's throwing me off, actually. That's dipole times. In fact, I should, whatever. So, yeah, so it's going to be P E times, and then the integral is negative cosine theta from theta to 0. So what that's going to be is work, when I put in the limits, I'm going to get PE. So that's one negative sign. But the other negative sign comes from the fact that the limits are flipped. So we're going to get minus, put theta in there, and maybe you want to do a theta naught or something. I don't know, but whatever. I just keep it as a variable. That becomes minus cosine theta. Well, just so that you're not confused, let me do that. Because that is the theta naught is the initial, whatever. Yeah. So cosine theta naught. Now then minus, that's the formulaic minus sign. But then, sorry, it's final minus initial, so it's 0 minus that. So final 0 minus, formulaic minus sign, but then I've got a minus cosine theta naught equals 0. Awesome. So that means it does, the electric field actually does positive work, which it does. And the work is positive because it converts the potential energy into kinetic energy as the thing rotates back toward its equilibrium position. So that all squares up. So the total energy then is going to be P, the total work done, that is going to be PE cosine theta. So positive work is done. Again, I do work on it. You know, we start from here. So work has been done on it and displaced. So it has potential energy in it. And now it's starting from rest. So as it moves back, it's speeding up. And that potential energy is being converted to kinetic energy as it approaches the equilibrium position and has its maximum kinetic energy at the equilibrium. And then now it overshoots because of the angular momentum, but now the electric field is doing negative work, taking that energy out and converting that kinetic, well, not taking it out, but converting it back to potential energy as it swings to the other side. So that's the work done, yes. And now the last step to show what the potential energy that it had was, is to then just use the general definition of potential energy. And the general definition of potential energy from mechanics says that work is equal to the negative of the change in potential energy, where the change in potential energy is defined as negative and as final minus initial. So U final, basically, and that's the potential energy at the equilibrium position. So I'm going to use that notation. Yeah, that's deceiving because theta naught seems, well, then I'll just put in 0. The potential energy, we define the potential energy when it's at its equilibrium position as 0, just like we do for gravity when something's on the ground. Because when I'm here at the equilibrium position, the electric field can't do work on it. So that was the final position. So I'll make that 0 because it's defined as such. It's like potential energy everywhere is defined as 0 at its equilibrium. And then minus the potential energy associated with that angle theta naught, where the initial angle it was. So did I screw that up? Now it's flipped around. I should get a negative sign out of that. Okay, what's happening? What's happening? Final minus initial. Final minus initial. Do we want to final minus initial? Also, the other thing is that this is not zero. It's, do I? Oh, because I've redefined that. That's right. It's not, I define the angle here, but I have to, if I had done that, the angle would, if it were aligned, yes, it's because I set my axis up like this with the initial. So I would have had to set the axis here, at the beginning, and now that's relative to the vertical. It's a different angle, right? I know. So theta, it doesn't really. So this is just, this picture is just the same as having it there. No, yeah, theta would be defined relative to that, so it's slightly different, right? No, 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 no. Okay, got it. It's just right here, the way I define this. It is defined as final minus initial, but I guess I started the problem midstream, so to speak. So integral of u final minus u initial. Sure. Oh God, it's so weird that it does that. Initial. Excuse me. The first time you made a sale, I I guess I was already in like the second cycle, because I was going back. But basically, if I'm starting at equilibrium, we can define that as essentially the initial position. So when I'm coming out here, that's you know in the first cycle, that would be the final position. So I think we can still define, we don't have to flip back and forth between final and initial with regard to our definitions for each cycle. It's kind of established in the beginning. So yeah. So then in that case, it flips around. Like we're defining the equilibrium position as the initial. So that's going to be, it'll be this minus u theta minus 0. So then we just get that the work done is equal to the negative of the potential energy. Well, it's really the change in potential energy. Or maybe that's all we need. Maybe that's another way to think about it. Because I've already, yeah, maybe that's a better way. I like that argument. I just thought about better. I like that better. We know that the potential energy is 0 at equilibrium. So the change is just due to the amount of potential energy it has, moving through that delta theta. So we can just start with equation 19 and just equate equate 19 and just equate them, 19 and 18. Two things that are equal to a third are equal to themselves. So then we can just say from 18 and 19 that P E cosine theta is equal to negative delta U. And so since U naught is 0, we can just say that then the potential energy function for this situation U is equal to P E cosine theta, or the negative of that. And so when you have two vectors multiplied by a angle between them, the cosine of the angle between them, that yields, of course, a dot product. So we can write equation for the final result then. It's going to be that the potential energy associated with the dipole moment immersed in an external electric field is equal to negative P dot E external. So whereas the torque is equal to the cross product, the net torque on that dipole is equal to the cross product between P and E. The amount of potential energy in that system whenever the dipole is displaced from equilibrium is equal to the dot product, the minus of the dot, the negative of the dot product between the dipole moment and the external electric field. So that's the result that I'm looking for here. I'm just curious. I'll look at your book and see what your book says about that. Well, that's the result. Let's just look and see what it has here in the book. I know that is the result, but something feels a little fishy for me. Second. Ooh. Sign issue that I have here. Right. Probably here in this kind of, yeah, dipole and an electric field. So yeah, they go and talk all the stuff I said. And then the final result for the dipole. Okay. Yeah, so that's torque. So you write it as a cross product. I see. They don't go to the extremes. They say vectors P and E are shown, and the torque acting on a dipole tends to rotate P into the dipole into the direction of the field, thereby reducing theta. In figure 2221, such rotation is clockwise. In our case, it would have been counterclockwise in my example. As we discussed in chapter 10, we can represent a torque that gives rise to a clockwise rotation by including a minus sign for the magnitude of the torque. Let's go back and look at that picture. Yeah, because it's just because they have it. So their axis is pointing in the x direction. They displaced it above the equator, so it's going to rotate clockwise back around. That's right. So they're defining that direction as negative. I didn't do that. Yeah. So we saw that. Yeah. So they're saying that their torque is also into the board if you do the right hand rule. And it's giving, because into the board is going to have a clockwise rotation, but they're defining that as negative. That's one way to think about it, because if you have x to the right, y up, then the negative z-axis is into the board. So that's one way you can think of it as negative. The other way, what they're saying is that this angle is decreasing as I go in a clockwise direction from this point of view. So I'm moving along essentially the negative angular direction. So the theta, the delta theta here is a negative quantity, and the sign of a negative quantity is the negative quantity. So that's where they're getting this thing from. So you might say your clockwise rotation, clockwise by including a minus sign, the magnitude of the torque, the notation. Yeah, so that's, so basically, the way that would translate with me is I would start the integral with a minus sign, which I started. What I did was put this thing into my, whatever this equation is, into my integral and work it out, 22.33. But what they put in the integral was 22.35. So they started with that negative sign. So in the end, they still get, and they get what I got here, but yeah, they're doing everything I said because they have the 90 down. But they went all the way to 90 degrees. So that was just convenient. I didn't go all the way down to 90 degrees because cosine or not, that's what we're going to get. Because what I have here is not quite right. Like I'm going, and they go from theta because they don't go back to zero. Because code would just get the total. Yeah, you want to do it in terms of the angle. Okay. Yeah, so they displaced it. If you go back up here, they basically displaced this thing 90 degrees so that F is perpendicular to P. I'll have to derive that way because, yeah, next time because, okay. It's just the limits that I set it up. I also made a mistake in here. It's not, so you get the same result, but it's just the way that I kind of set it up. Because what I noticed that this is not zero, that's one. Actually, it would be PE. So as opposed to me coming from some arbitrary point and going back to equilibrium zero, what they did is they went all the way to 90 degrees and basically, went from 90 degrees, but they didn't go to zero. They didn't go all the way through the 90 degrees. They stopped at some arbitrary point within there called theta, just to show that amount of work we need, because the extreme value there gives something that's kind of off. And it's not zero, it's PE, but it still would be negative. But yeah, PE minus a D minus a cosine theta. So I just, yeah, minus a constant. Yeah. Yeah. Well, I'm going to move on. I think I'm going to get on to my example of charge of the of Coulomb of Gauss's law. So I'll let you kind of look at what they do there in the book. I guess I could clean this up though. I have this in your notes. So we gotta start here. The end result is going to be the same, but here this is not quite right. Start here and say something like W is equal to integral of negative P E sine theta d theta. And we can say because either the torque is pointing along the negative direction, or technically because you're putting in the magnitudes, that's not really um, the way you say it, but maybe because angle is decreasing because you're going from some angle theta. Well, we can expand. So I can displace it to a max to a 90 degrees. So I could say like pi over 2. back to some arbitrary angle 0. Sorry, some arbitrary angle theta. Okay, that's how to remember that in the future. Yeah. And so in this case, it actually would be 0 in the next interval then, because 15. So I'm going to get work is equal to, so this stuff comes out, negative PE, and then that's going to be an integral, because cosine. So we get a cosine of theta goes from pi over 2 to theta. And final minus initial, yeah. So I'm going to have negative PE. Final is cosine theta. Cosine theta minus cosine pi over 2. And that's going to get me 0. Cosine pi over 2 is 0, in fact. Then that leaves me with minus PE cosine of theta. Now the minus sign is just for that specific example. So that's going to get me what I want, because I'm going to be putting in a minus over here. So minus is here, right? Look at that again. Getting bogged down in these little things. Took more time than I really wanted it to. Always with minus sign. Yeah, petitioners use negative cosine. But then there's 2 more negative signs, isn't there? Yeah, there's 2 more negative signs. So that's the 3 negative signs I was talking about. This one, and then we're going to get, this is 1. And then the general definition of potential energy is 1. But then isn't that 1 in here? Well, when we actually do that out, you see. You see, you got the negative there. They kind of skipped over that, I think. Now maybe I'm overthinking it. But 20. So work is equal to the negative of, but it's final minus initial. And according to this, final minus initial. For this problem, final minus initial. That's going to be u at theta minus u at pi over 2. The potential energy at pi over 2 is not 0. I've got more potential out there than I do at theta. So you just kind of jump to the next step here and actually show. Oh, well, they put it up there. Okay. That is the. But then they didn't put the negative sign in. So that negative comes from the general definition. It's the same negative sign. So you're using the positive value for torque. So they do that, they get. So that negative sign comes from. So they do get a positive, but then they define. So if I had done it as a cosine, then I come over. So that's implying that. But it's not the work at that position, it's the change in work. Got it, yeah. So yeah, the potential energy at this point actually is zero. Yeah. So that the change in potential energy is then therefore negative U naught, or U theta. And then U theta is the, so so again, third time's a charm. I was right. It's not a negative torque, it's positive, like I said. It's just that I misdefined that. Sorry, I got to get these things right. I don't know why I got twisted up on this at some point today, but I got to get it right. It's going to stay twisted in my head. So going back again, going back again. Put in a positive here, okay? So there's no negative sign associated with that. Positive, positive, positive. And this same thing, I'm just doing it slightly different than what they kind of did a couple steps at once. I'm breaking it down. So we get the torque from here, put it in here, and we get PE sine theta, d theta. Now, this is a little different than what I had done. In other words, it's kind of like what they're saying is, I'm going to go ahead and put the axis like they did. Or it doesn't matter. I had my axis straight up and down. I'll keep it like that. But then I'm going to change my field so that we start out at the equilibrium position. I'm going to place my field like this. And so when my dipole is pointing like this, it's at equilibrium, right? But then I displace it to some angle theta. Well, what they're saying is, if I want to figure out the potential energy it has at that point, I displace the thing all the way to 90 degrees, and it's just based on how potential energy is defined. And the potential I have at that point is equal to the potential energy that I acquire from going from pi over 2 degrees to that point. Yeah. Because the reason is because I was, it's because of the decreasing angle. I see what they mean by that. Because cosine, no matter how you set this up, the cosine of 0 is always going to be 0 at 90 degrees when you're displaced to a maximum. So you can't really consider the potential energy at that point. What you have to consider is the change in potential energy from the 0 mark to wherever it is. It's a little bit counterintuitive from like the gravitational scenario. Yeah. The torque is a maximum, but the potential energy is a minimum. And with gravity, whenever the force of gravity is a maximum, the potential is a maximum at that same point. And where the force is 0, the potential energy is 0. Here, it's kind of flipped. Here, where the torque is 0, mathematically, the potential energy is a maximum. And here, where the torque is maximum, the potential energy is 0. You know what? All these years, I never thought about that. I never thought about that. Wow, physics is amazing. It's always these like an onion, there's level after level after. I never thought about that for this situation. That's why that's the case. So it's more a mathematical thing and not a physical thing, but it does have some physical implications in the way that you describe it. And that's the issue that we're having here. In my opinion, that's how I would say it. But this is right. So all of that was right, actually. Positive. And so now, when I put the units in, now, so what's happening is I'm not going, it's kind of different in my mind. I'm going from this place to just some arbitrary point there. And so we're defining a potential energy at that point, or the change in potential energy at that point, to get to that point. Well, basically, actually, it's the change in potential energy to go from here to here, basically. Actually, is what it is, because out here is 0. So it's really not, yeah, it's a little bit confusing, but it's because of the way that 0 potential is defined away from the equilibrium point. That's weird. Yeah, I never thought about that. Anyway, we go through, we calculate this guy, and we get cosine, yeah. So you get this positive over there. So now, that was right, it's positive, but it's how I had this defined. Yeah. So that work is equal to the negative of, now they just put the U in there, so they didn't kind of deal with what I'm kind of trying to explicitly show here. I forget what the equation number is, but they had something set up that, and they did it all at once, right? They said U is equal to, or U is equal to negative W, which is equal to a negative integral tau d theta. So I'm actually not doing it all at once. I'm working out the integral, and then I'm going to equate the result of that work to delta U. And I guess I could just make this U. I could make it easier on myself. But it's not really U. It's delta U is the actual theory, and so, or equation. So then you got to define a zero potential, and that's where it goes out. So that's where I was having trouble because I was going from here to here, defining as initial and final. But I think what you have to do is go from here to, well, actually what they did, I guess they did go from here to here because they say, because it's cosine now. And so final minus, yeah, I don't, even now I don't, that's strange. Well, at this point, I'm just going to do what they did. They just, I guess, called one of them zero. I guess to make it work out, it would have to be, if I were here and I rotated it to here, um, that would be u at theta minus u at, you know, theta equals zero, which we call that zero. And then that gives me the minus u with w, which is p e cos theta. So that would then define u as equal to the minus p e cosine theta, which is equal to minus p dot e. Yeah, I gotta work that out and make sure that I'm yeah, that's what the argument that they use, but something just seems a little bit off in the way that we set up the limits there. Should be able to work it out specifically. Somehow I'm missing something, I think. I don't know. But that brings us to the end. So yeah, I probably will go ahead and post some things, you know, these Gauss's law problems. I can post them over the weekend, put some extra stuff in. And yeah, so that fully wraps up information from chapter 21 and chapter 22. I didn't put out the